This recording will cover electric potential. I won't be doing any of the in-class exercises in the recording, and some of the quick check questions I'll also skip and cover in class. So the goal of this chapter is to calculate and use electric potential and electric potential energy. And we're going to be seeing what the difference between those two is as we go through the chapter. So we first learned about gravitational potential energy in the first semester. We also learned first semester that when you do work on an object, it changes that object's energy, either potential or kinetic. And so it says you lift a book at constant speed. Which statement is true about the work done by your hand and the change in the book's gravitational potential energy? Well, when you lift a book up, you are increasing its gravitational potential energy, which is related to the distance above the surface of the earth. The formula was mass times gravity times height. And so the work that you do against gravity to lift it to a certain height is equal to that book's change in gravitational potential energy, which is a number that is greater than 0. So the answer would be C. So now we're going to talk about electric potential energy and electric potential. So chapter 20, or the chapter on electric fields and forces, talked about the electric force. And so now we're going to look at the potential energy associated with electric forces. And then we're going to relate that to something called electric potential. So we learned that back in the first semester that there's a law called the law of conservation of energy, which says that the total sum of potential and kinetic energies of a substance or of an object remains constant. So when you lift a book above the surface of the earth, you're giving it a high potential energy. And that then if you drop that book as it falls, that potential energy is used or is converted to kinetic energy. So we talked about this, that as you do work on the book gains gravitational potential energy. We also looked at a spring, and as a hand does work on a spring to compress that spring, it gives it spring potential energy, which was 1/2 K times X. I think 1/2 K times X squared, I mean. So it says, now we're going to look and see how we can apply that concept of giving something energy by moving it through a certain distance, which is what work is, force times distance. We're going to apply that to electricity. So it says if you have a test charge or a charge, and you are trying to put it closer to positive charges, and the test charge is positive. Like charges repel, so it's going to take work to push it closer to the test charges. So you're going to go from an area of low potential energy to high potential energy. And it's going to take work on your hand to get it from low to high potential energy. So the change in electric potential energy is equal to the work. Now obviously we're not really doing work on a charge. This is just a hypothetical example. So it says, I'll do this quick check problem in class. It's a little bit easier to explain as I do it in class. So in the electric field model, we say the source charges alter the space around them, which is what creates the electric field. And it's the electric field, not the source charges themselves, that exert the force. And we said that an electric field is present whether there's a point charge or a test charge there to feel it or not. We're going to apply similar reasoning to electric potential energy and learn that electric potential energy is present whether or not there's a charge to experience that potential energy or not. So now we're going to do a hypothetical example. We're going to say we're going to take a charge and it has a value of 10 nanocoulombs. It could be anything. And we're going to say at point A, its electric potential energy is 0. And so in order to measure its electric potential energy at point B and point C, we're going to have to calculate how much work it takes to move this charge from A to B and then from A to C. And again, this is a hypothetical example. These values are going to be given to you. So let's say it takes 4 microjoules of energy to move the charge from A to B, and 6 microjoules of energy to move the charge from A to C. And so that would be the amount of work done on the object. And so we would say it would have a potential energy at point B of 4 microjoules and a potential energy at point C of 6 microjoules. Now, if you were to change the charge to 20 nanocoulombs, so it was 10, now we're doubling the charge. It would make sense then that it's going to take more work to move it from A to B and B to C. And it would, since we're going to be overcoming twice the force, it's going to take twice the amount of work that it did to move the 10 nanocoulomb charge. So it says a charged particle's potential energy is proportional to its charge. The higher the charge, the more potential energy. But it doesn't matter what the charge is. The ratio between the amount of potential energy that it gets and the charge is the same. So this is looking at moving the charge to point B. So for a 10 nanocoulomb charge, we said it took 4 microjoules of energy. And we said if we doubled that charge, it would take twice as much energy. If we cut that charge in half, then it would take half of the amount of energy. And so if you divide 8 microjoules by 20 nanocoulombs, or 4 microjoules by 10 nanocoulombs, or 2 microjoules by 5 nanocoulombs, you get the same amount, 400 joules per coulomb. So all of the ratios are the same. So that ratio is it's the amount of potential energy that any charge would have if it was placed at the same point. And in your lab, you're going to learn to relate this to potential energy. So let me give you an example. So let's say this is a hill, and I'm going to draw a line and at a certain height above the earth. At any point along the line, the same object is going to have the same potential energy. And we know that the gravitational potential energy is equal to mass times gravity times height. And I'm going to write mass times, that's not a very good, gravity times height. So gravity times height is going to be the same along this line. What's going to change the amount of potential energy is going to be the mass. So the larger the object, the more gravitational potential energy it has. But gravity times height is going to be the same along this line. So this value for a charge is the same as gravity times height. What's going to change the amount of total potential energy is the size of the charge. But the ratio of energy to charge is going to stay the same. And so we're going to give that ratio a name. And that ratio of energy to charge is called the electric potential. And again, this is the electric potential energy that any charge would have if it was placed at the same point. So it's like saying it's the same height, and mass times, or gravity times height, is the same. at all the points for the same distance above the surface of the Earth. So this is saying that this is the potential, that value V is the same, and it's the ratio of energy to charge. And then when you multiply that by the charge, you get the amount of potential energy. So that tells you the relationship between the electric potential and electric potential energy. So electric potential is abbreviated V. The SI unit of V is the volt. So the electric field tells us how a source will exert a force on Q. The electric potential tells us how the source charges would provide Q with potential energy. And so it says, notice the similarity of electric potential energy to force is equal to Q times electric field. So this looks like this equation is set up the same way. Here we have potential energy is Q times V. Here we have force is Q times electric field. And so it says, like the electric field, electric potential is present at all points in space. And it's present whether a charge is there or not to experience it. So there's a certain electric potential at point B and point C. The potential energy that a charge will have at point B or C depends on the size of the charge, but that potential is there whether or not a charge is there or not. It says when a charge moves from point A to point B, it moves through a potential difference, which is just the difference in potentials between points A and point B. And we can call that delta V, which means the change in potential. So the change in potential energy is equal to Q times delta V, the change in potential. And these are some typical electric potentials at certain places. So in the cells in a human body, there's an electric potential of 100 millivolts. In transmission lines, there's an electric potential of 1,000 kilovolts. A battery has an electric potential of 1 to 10 volts. So those are just some different electric potentials. And again, those are areas where a charge will experience potential energy. So it says when two charges are brought separately into the vicinity of a fixed charge Q plus Q. Or it says two charges are brought separately. So first of all, and here's the fixed charge. So in situation 1, you have a positive charge and it's brought close to Q. In situation 2, a negative charge is brought close to Q. The positive charge is removed and it's placed with a negative charge. And we want to know about the electric potential energy at in situation 1 and 2. Is it the same or is it different? Okay, so like charges repel. So in order to move this charge from point 1 to here, from here to here, we're going to have to it's going to take some energy. When the negative charge, which is going to be attracted, it has a greater potential energy here actually than it does here because it's attracted. It wants to be in this position. So the electric potential at point A is actually going to be greater for the positive. The electric potential energy is going to be greater for the positive charge than it is for the negative charge. Now, this is looking at the same situation, except now they're looking at the electric potential. And remember, electric potential is just the potential for creating potential energy. And that does not depend on the charge. That is independent of the charge. That only depends on the source charges. So the electric potential is going to be the same at this point, whether there's a positive charge here or a negative charge here. The potential energy will be different, but the electric potential will be the same. So the answer is C, the same for both. Okay, now we're just going to very quickly look at sources of electric potential. So it says, can you create an electric potential? Well, let's say you have an uncharged capacitor and you're moving a charge from point A to point B. Now, if there's no charge on either plate, the potential energy of this charge is going to be the same at point A as it is at point B. So it takes no work then to move it from point A to point B. And so we would say then that the potential difference is the same, or is zero. The potential at A and B are the same because there is no charge. Now, let's say you charged the capacitor, and so you had one side that was negative and one side that was positive. So now you have a separation of charge. And now if you want to move this charge from point A to point B, you're going to have to do work on it to get it from point A to point B. And so if you have to do work on it, it's going to increase the potential energy. And the total amount of potential energy is going to be related to the charge, but the potential we said was not related to the charge. It's only related to the source charges. So whenever you separate charges, you create a potential difference. So a potential difference is created by separating positive charge from negative charge. So it said metal wires are attached to the terminals of a 3-volt battery. What is the potential difference between points 1 and 2? Well, you have a separation of charge, so it would be 3 volts. Metal spheres are connected by a metal wire. What quantities do spheres 1 and 2 have in common? Well, there's nothing in between them to separate charge. So they're going to have the same potential. They're not going to have any charge. And if there's also no electric field because there's no charged particles. Okay, so it says when you shuffle your feet across the carpet, you pick up charge from the floor. There's a potential difference between your body and something metal nearby, and it's enough to create a spark as the excess charge moves from higher potential to lower potential. Now, a battery uses a chemical reaction to separate charge. The potential between these two terminals is 9 volts. So different batteries have different potentials. And we'll talk more about how a battery separates charge in later chapters. Your cells can also separate charge because they participate in ion exchange. Not going to go into this in any great detail, but that's how you have an electric potential in your cell membrane. We can measure electric potential using a voltmeter. We'll get a chance to do that in reality when we do our electric field mapping lab. And the way a voltmeter works is just it measures the potential difference between these two inputs. Okay, so now we're going to talk about electric potential and the conservation of energy. So we defined, or we came up with the equation that electric potential energy is equal to charge times potential. And we said that although they're related to one another, they are not the same thing. It says when a positive charge moves from a region of high electric potential to a region of low electric potential, its potential energy decreases and its kinetic energy increases. So just like when you have a book and you raise it above the surface of the earth and then you drop it, as it falls toward the earth, its potential energy decreases, but its kinetic energy increases. So at the highest point in its path, its potential energy is a maximum, kinetic energy is 0. At the lowest point in its path, right before it hits the ground, its potential energy would be 0 and its kinetic energy would be a maximum. And that's the law of conservation of energy. So it says electric potential is created by the source charges, and it's present whether or not a charge is there to experience or not. Electric potential energy is the interaction of a probe charge or an external charge with the source charges, and it depends on the size of the charge. Okay, so this is the law of conservation of energy. We know that initial kinetic energy plus F stands for final. Final kinetic energy plus final potential energy is equal to initial kinetic energy plus initial potential energy. And so if instead of writing U as the symbol for potential energy, we write Q times V, which is our formula, it changes the equation to this. So the equation for kinetic energy is going to be the same. And just as a reminder, kinetic energy is equal to, you should remember this from first semester, 1/2, sorry, this is very tedious to write with this thing, 1/2 mass times velocity squared. So we're going to be talking about potential and velocity. So velocity is a lowercase v, potential is an uppercase v. So make sure you don't confuse those when they're both present in the same equation. Okay, so if we look at this and we know that the charge is not going to change, so Q will stay the same. V final minus V initial is delta V. K final minus K initial is delta K. So we can rewrite that as delta K, the change in kinetic energy, is equal to negative Q delta V. So when delta K is positive, the particle speeds up as it moves from higher to lower potential. When delta K is negative, the particle slows down as it moves from lower to higher potential. All right, so it says a positive charge speeds up as it moves from higher to lower potential. So remember, if a positive charge is going to be attracted to, it wants to move toward negatives. So it's going to move toward an area of lower potential. And as it moves from 500 volts to 400 volts, it's going to speed up because it has a higher potential energy here and a lower potential energy here. Now, at any of these points where you have these dashed lines, these are points where the potential is the same, and they're called equipotential lines. Now a positive charge is going to slow down as it moves in the opposite direction. So as it's going from a lower potential to a higher potential, its potential energy is going to increase and its kinetic energy is going to decrease. And again, we're not going to do any in-class exercises here. I will do them in class. Now, electric energy can also be transformed into other types of energy, like thermal energy, just like we learned that there's thermal energy in mechanical energy as well. So we are not going to really do any formulas calculating the amount of thermal energy. Okay, a positive charge moves as shown. So a positive is going from a negatively charged plate to a positively charged plate. So its potential energy is going to increase as it goes from, we'll call where it starts A and where it ends up B. So as it goes from A to B, its potential energy will increase, therefore its kinetic energy will decrease. So the answer would be C. A positive and a negative charge, we're going to skip this one for right now. A proton is released from rest at the dot. So it's a proton. A proton has a positive charge. A proton is going to spontaneously move in a direction that lowers its potential energy. So it is going to move toward the negative potential. And as it moves downward, its speed is going to increase and its potential energy is going to decrease. So the answer is going to be E. It's going to move downward with an increasing speed. Think of this as being a hill, and you're dropping a book from the top of the hill. Its velocity is going to increase until it hits the ground, and its potential energy will decrease. If a positive charge is released from rest, it moves in the direction of, it's going to move toward the lower electric potential. So it's going to move in the direction of the lower electric potential, which is D. I just want to briefly introduce another unit of energy that you'll sometimes encounter, and it is the electron volt, or EV. And it's abbreviated with a lowercase e and a uppercase V for volt. So an electron volt is a unit of energy. It's not a unit of potential. So it's solved by multiplying the charge on an electron, which is the fundamental charge, times the potential. So this is the fundamental charge times the potential, and so it's a small unit of energy, and that is an electron volt. But sometimes you'll see energy in electron volts, and then oftentimes when you go to put it into an equation, you're going to need to convert it into volts. But it's an not into volts, into joules. But remember that an electron volt is not a unit of potential, it is a unit of energy. Okay, so two protons, one after the other, are launched from point 1 with the same speed. They follow the two trajectories as shown. And it says the proton speeds at points 2 and 3 are related by. All right, so in going from point 1 to point 2 or point 1 to point 3, the change in potential energy is going to be the same. And so think about this as when we talked about how potential energy changed in the last chapter. Whether you walked up a hill or took a ski lift up a hill, once you got to the same point, your potential energy, your change in potential energy was the same. So likewise, their change in kinetic energy is going to be the same. They're both going to lose the same amount of potential energy and gain the same amount of kinetic energy. So their velocities then will be the same at both of these points. So the answer is B. V2 equals V3. An electron follows the trajectory as shown from point 1 to point 2. So if it's going from here to here, it's going farther away from the positive charges. And so to do that, you're going to have to give it potential energy because it doesn't want to go here. It's going to take energy to get it to move from point 1 to point 2. So if you have to put potential energy in, that's going to reduce the amount of kinetic energy and reduce the velocity. So V2 will be less than V1. So the answer will be C. All right, now we're going to learn how we can calculate the electric potential. All right, so in the last section, or a couple of sections ago, we learned that potential energy, U, electrical potential energy, is equal to charge times potential. So if we rearrange this equation, this would be, and this should be a capital V. Potential is equal to potential energy divided by charge. So if you want to find the potential, you would just find the potential energy and then divide it by the charge. So we're going to look at three cases of how we can find, or three different cases where we will calculate the electric potential. We're going to look at a parallel plate capacitor, and we first looked at those in the last chapter. We're going to look at a point charge and then at a charged sphere. And we'll learn how to calculate the electric potential of all of those things. So we know that a parallel plate capacitor creates a uniform electric field. And the electric field always goes from positive to negative. And so if we were to visualize taking a positive charge starting at the negative plate and pushing it toward the positive plate, it's going to take potential energy to do that. And the amount of potential energy that we use is going to be equal to, or is going to be related to the distance that we have to push it to get to a certain point between the plates. So it says let x equals 0 at the negative plate and x equal d at the positive plate. So it says let potential energy equals 0 at the negative plate, and then it's going to be a maximum at the positive plate. So it says the charge's potential energy at any other position x is then the amount of work necessary to move the charge from the negative plate to that position. So that's what I said. If it's going to take work to move it from here to here, work is equal to force times distance, so it's going to be related to where you move it to within the parallel plate capacitor. So the electric field points from positive to negative. So, and we know that the force from the electric field is Q times E, and in this case Q is the force that Q is the charge. It's the force that a charge feels from the electric field. We also said that work was equal to force times x, or force times distance. So if force is equal to Q times E, then we can substitute force, Q times E for force in this equation, and you get that work done is equal to Q times E, the electric field, times x, the distance. So it says, consequently, the electric potential energy is equal to Q times E, and E again is the electric field times x. Now, if we want to relate that to potential energy is equal to, not potential energy, if we want to relate it to potential is equal to potential energy divided by Q. And we said that, if I'm going back here, that U was equal to Q times E times x. So if you divide, it's kind of hard to show on here how we derive this formula. So we know that U divided by Q is equal to, and that's a U, not a B, is equal to E times x. So all I did was divide both sides by Q. So U divided by Q, so I divided U by Q, is equal to E times x. All right, now going back here. So we said U divided by Q was equal to E times x. We also know that potential is equal to U divided by Q. So potential is equal to E times x. This was the equation, Q divided by epsilon naught times A. That was the equation for the electric field of a parallel plate capacitor times X. And so X is equal to D, the distance between plates. And so the potential difference in a parallel plate capacitor is equal to E times the distance between the plates, which is equal to Q times epsilon naught times A times the distance between the plates. So that is the potential difference of a parallel plate capacitor. And so if you know the electric field and you know the separation between the plates, you can use that to get the potential of a parallel plate capacitor. Now, if you want to know what the potential is, so the maximum potential would be when you go from one plate to the other. But if you want to know the potential at any certain position, that's just equal to that position divided by D, which is the separation between the plates, times the potential of the capacitor. And we'll do a couple of problems, or at least a problem, where we'll look at that. I think I just went backwards. Okay, yes, there we go. All right, so we can pictorially represent potential inside a parallel plate capacitor in 3 ways. So you could do just a graph of potential versus the potential versus distance. So we can see that when the separation when you're at one plate, there is no potential. As you go to X, the potential is going to increase, and it's going to be the maximum at the when the plates are, or at the separation between the plates. So at the positive plate. I'm not saying that very well. You can also look at equipotential surfaces, or equipotential surfaces, which are surfaces where the potentials are the same. So the potential is 0 at the negative plate, it's 1.5 volts at the positive plate, and then at certain distances in between those two, it's going to have equal potentials. And then we can do what's called an equipotential map, where instead of showing actual surfaces, you just visualize or represent the surface with little dashed lines, and those are equipotential lines. Okay, so now we're going to look at the potential of a point charge. And so we're going to look at a single charge that is generating an electric field, and we want to find the electric potential that a second charge is going to feel when it is, or not is going to feel, but that a second charge is going to experience when it's placed at a certain distance away from the initial source charge. So we're going to choose the potential energy to be 0 at a point infinitely far away from the point charge. All right. So here's our point charge, and here is our probe charge. And so we're going to say that when we're way out here, potential energy is 0. And so it's going to take work to move closer to the source charge. Now, work is equal to force times distance. Coulomb's law says that force is equal to Q times Q prime times K divided by R squared. So work is force times distance, so distance is going to cancel out. So it's just, when you want to get potential energy, it's K times Q prime over R. And that is the electric potential energy of 2 charges separated by a certain distance. So potential energy is going to go down the farther away the charges get from one another, but it's not an inverse square law. It just is an inverse law. And it's because it's not force, it's force times distance. And so distance cancels out. So one of the distances cancels out. All right, so it says in the cases where Q and Q prime are opposite charges, the potential energy of the charges is negative. And that's because Q prime wants to move towards Q. So it's accelerating. Q prime has more potential energy out here, less potential energy out here. It's the opposite of a positive charge. So to figure out the potential, again, potential is equal to potential energy divided by Q prime. So now Q prime is going to be out of the equation. And so potential is going to equal K, Coulomb's law constant, times Q, which is the source charge, divided by R, which is the distance away from the source charge. Now it says, what is the ratio VB to VA of the electric potentials at the 2 points? So again, this is not an inverse square, it's just the inverse. And we know that the farther away, the lower the potential. So if the potential at point A is 1 and point B is 3 times as far away, the ratio of VB to VA is going to be 1 to 3. It's going to be 1/3 the potential at B that it is at A. Now, just like we did with the parallel plate capacitor, we can represent this in 3 ways. So we can do a potential graph, which shows that the potential decreases with increasing distance. We can do a 3-dimensional equipotential surface diagram. So think of the layers of an onion, and each layer has equal potential. Or you can do an equipotential map, which is just 2-dimensional, and it shows equipotential lines by dashes. All right. Now we're going to look at the electric potential of a charged sphere. So this is the 3rd case. We've already looked at the parallel plate capacitor, point charge, and now we're at the charged sphere. So the electric potential outside a charged sphere is the same as the electric potential at a point outside a point charge. So electric potential is equal to K times Q divided by R, except now Q is the sphere, the charge of the sphere, and R is at a distance that's greater than the radius of the sphere. Oops, trying to advance the slide. Okay, so if you're at the surface of the sphere now, we're going to call that V sub 0 or V prime or V sub 0. That's the potential at the surface of the sphere. So that's at the point where R, lowercase r, is equal to the radius of the sphere, which we're going to call uppercase R. So that's equal then to Q divided by 4 pi times epsilon naught times R. And again, you can, the book just chooses to express it this way, but you can use K. Again, remember, K is equal to 4 pi, 1 over 4 pi times epsilon naught. So you don't have to use this. You can use K. I think they're just, because it's a sphere, they're choosing to use epsilon naught. And I didn't mean to go forward. Okay, so the charge for a sphere of radius r then is 4 pi times epsilon naught times r times the potential at the surface. And then if you want to look at the potential outside a sphere, so at a certain point away from the sphere, that's equal to the radius of the sphere divided by the distance that you are away times the charge at, or the potential at the surface of the sphere. So the potential decreases inversely with the distance from the center. So again, uppercase R is the radius of the sphere. R is the distance from the center of the sphere. V sub 0 is the potential at the surface, and then you can use that to calculate V. at any point outside or a certain distance away from the sphere. All right, so again, at any point away from the sphere, the potential is equal to the radius of the sphere divided by the distance from the center of the sphere times the potential at the surface of the sphere. We'll do this one in class because it's easier to do when I can write things on the board. Now, this does apply to ionization energy, which is the amount of energy that it takes to remove an electron or to ionize an atom. And it says removing an electron leaves a positively charged ion behind. You can assume that the electron is at the surface of the sphere, which is about equal to the size of the atom, and it requires energy to separate these two charges. We're not going to say a whole lot more about that. Now, when you get the electric potential of many charges, it's just equal to the sum of the electric potentials due to each charge. And R is the distance away from the charge. Now, unlike electric fields or forces, electric potential is a scalar quantity. So when you're adding together different electric potentials, you're just adding them as scalar quantities, and direction is not important. All right, we'll do some of these again in class. So this is actually the next section where we're going to connect potential and field. And this is what we did in lab if you've done the field mapping experiment. If you have not done the field mapping experiment, this is what you will be doing in lab. We'll be mapping potential, and then we'll be using that to construct an electric field. So we're going to look at a charge, and these are equipotential lines. So one way to visualize this is, let's say, let me draw again. Oops, didn't draw anything. So let's say, oh, that's not a good. We have the surface of the Earth. So I'm going to draw it lower. And then we have a line that's equal distance from the surface of the Earth. So I'm just going to draw some dots at a position equal distance from the surface of the Earth. So if you have an object that is moving along this line, its gravitational potential energy doesn't change. Think of if you are you pick up a book. Initially, when you pick it up, its gravitational potential energy changes. But if you move forward with the book, all you're doing is carrying the book. You're not changing the potential energy of the book by moving it in horizontally. So likewise, when a charged particle moves along an equipotential line, it's not gaining or losing any potential energy. The potential energy here is the same as the potential energy here. So there's no change in potential energy, therefore no work is done moving a charge from this point to this point. Now, you will have also learned in the lab that the electric field is perpendicular to the equipotential lines. I need to go back a few. Oops. Sorry. So we talked about, I just was on this slide and I stopped and then I picked up. So I needed to find where I was. But we know that the electric field is perpendicular to the equipotential lines. That's something that has to be true if no work is done when a charge moves along an equipotential line. Kind of like gravity is perpendicular to the motion of a person walking along the surface of the earth. And so that enables you to not do any work because you're not changing the potential energy. You are only moving it from point A to point B at the same potential. So you're not changing the potential energy. All right, so it says the electric field causes a charge to speed up as it falls toward a lower potential. So if the electric field was working on this charge, that charge is going to, it wants to go from higher to lower. And as it does so, it's going to lose potential energy. And therefore, it's going to, its speed will increase. If you go in the opposite direction, it'll gain potential energy and its speed will decrease. So we are going to be able to calculate the magnitude of the electric field by looking at the amount of work that it would take to change the potential of that particle, of that charge. And we're going to combine the equations that work is equal to the change in potential energy, which is equal to charge times the change in potential, with the equation that we learned earlier for electric field. And we will find that the magnitude of the electric field is equal to the change in potential divided by distance. So the change in potential divided by distance. And that is the electric field strength in terms of potential differences between two equipotential surfaces that are at a certain distance apart. So just to summarize, or just to state some important points, the electric field is perpendicular to the equipotential surfaces. So you can map an electric field by drawing lines that are perpendicular to the equipotential surfaces at a variety of points. The electric field always points toward in the direction of decreasing potential. So if this line was at 9 volts and this line was at 7 volts, the electric field is going to point that way. And the field strength is inversely proportional to the spacing between the equipotential lines. So the closer together the equipotential lines, the stronger the electric field. The farther away the equipotential lines, the weaker the electric field. Okay, so it says a proton starts from rest at point A. It then accelerates past point B. The proton's kinetic energy at point B is, well, the change in potential is 100 volts, and so its kinetic energy then will be 100 electron volts. Because kinetic energy is equal to the change in potential energy, and that is its change in potential energy. So it says below are 3 important arrangements of charges. Both electric field lines and equipotentials are shown. So here's the electric field of a point charge. These would be the equipotential lines. So the equipotential lines are closer. The closer you are to the point charge, they get farther away the farther away you go, because we know the magnitude of the electric field decreases the farther away you get from a point charge. This is a dipole. We mapped this in class. We know that the electric field is stronger the closer you are to one of the charges, and it gets weaker the farther away that you go. The magnitude of the electric field is actually 0 in between the dipole. In a parallel plate capacitor, the equipotential lines are evenly spaced, and the potential has to do with how far away you are from the positive plate. The electric field is also very uniform. In all cases, the electric field lines are parallel to the equipotential lines. So It says at the midpoint between these two equal but opposite charges. Okay, so here's the midpoint between these two equal but opposite charges. So the electric field is going to point, it always goes from positive to negative, so it's going to point from left to right, but the electric potential is actually 0 between those two. It says a particle follows the trajectory shown from initial position I to final position F. The potential difference, it doesn't matter how it got there. The potential difference is only related to it, to where it started from to where it ended up. So the difference between F and I is negative 50 volts. And so that answer is D. Which set of equal potential surfaces matches this electric field? So we know the equal potential lines are closer together when the electric field is stronger. And the electric field lines are, or the electric field vectors are larger where the electric field is stronger. So the electric field is stronger here than it is here. So we want our equal potential lines to be closer here than they are at this end. So that is going to be case C, because it shows the equal potential lines closer here than they are here. And again, how do we know it's going from, we know it goes from positive to negative. So this has to be at a higher potential than this end. This end is at a higher potential than this end. So that's why it's 50 is on this side and 0 is on this side. Okay, so the next section is on capacitance and capacitors, and I actually have another video that goes over capacitance and capacitors, and so I'll make that video available for you to watch. So you are now done with this video.